Hello, Algebra 2. Today we're going to start our new unit on statistics. Statistics is a branch of math concerned with collecting, organizing, and interpreting data. And these data are represented by graphs. So one graph that we use in statistics is the normal distribution curve. So the normal distribution, it's a very important statistical data distribution pattern. It's occurring in many natural phenomena. So we use this a lot in things such as height, blood pressure, lengths of objects produced by machines. It's also used for standardized test scores like SATs or ACTs. So certain data, like height, like blood pressure, like SAT scores, when graphed as a histogram, it creates a bell-shaped curve. And we call that the normal curve or the normal distribution curve. And it looks like what's on your screen. Okay, normal distributions are symmetrical with a single central peak at the mean or the average of the data. So if you look at the one here, they put numbers at the bottom just as an example. Let's say this is some sort of standardized test score. So that would mean that the mean or the average would be right in the middle. So the mean or the average of this test score must be 75, whatever this test score is. The shape of the curve is a bell shape. 50% of the distribution lies to the left and 50% lies to the right. So 50% of the scores are above 75, 50% of the scores are below 75 in this example here. Okay. The mean and the median are the same in a normal distribution. So in the example above with the scores, 75 would be both the mean and the median. And we sometimes say that the normal distribution is a family of distributions because they can all normal distribution curves can look a little different. See, we have all the ones I just circled. Some of the peaks are higher, some of the peaks are lower. They're all normal distributions. So some basic things about normal distributions are it's symmetrical about the mean and the median and the mode are all the same. The mean divides the data right in half. So those are some important things to keep in mind. Okay, so this is what our normal distribution or our bell curve looks like. Okay, if we look at the middle is the 0, that's where we're going to put the mean. Whatever mean we're talking about, or the average, that would go right there where I just made that purple line. So let's just say as an example that the math SAT scores can be normally distributed, and the average math SAT score is a 500. Okay, so I'm going to put that 500 right under the 0, just so we can kind of see how this whole thing works. And let's say the standard deviation is 100. Okay, so that's two things that you need to be told. You need to be told the mean, and you need to be told the what a standard deviation is. So if the standard deviation is 100, that would mean to get to the one standard deviation above, that would be a score of 600. Okay, one standard deviation below would be 500 minus 100, since I told you that the standard deviation was 100, so it would be 400. If we wanted to keep filling in, if I wanted to go to 2 standard deviations above the mean, well, we know that 1 standard deviation above is 600, so 2 standard deviations above would be 700. 3 standard deviations above would be 800. Okay, if I want to go back, one more standard deviation below the 400s, that would be 2 below, would be 300, and one more below would be 200. Again, I kind of made this up as an example, but the 500 represents the mean or the average. Okay, so if you take a look at the chart, and if we look between -1 and 1, that's 1 standard deviation below, all the way to 1 standard deviation above. They give you percentages of the population that fall in there. So if we were to take from 1 standard deviation below to 1 standard deviation above, we would need to add up all those percentages. So if you add up 15.0 plus 19.1 plus 19.1 plus 15.0, you will get exactly 68.2%. So what that means is, if this was the example with the SAT scores, 68.2% of the people who took that SAT math got between a 400 and a 600. 68.2% of the people got between a 400 and a 600. We say that their scores were within 1 standard deviation of the mean. If I wanted to go out a little bit further and go 2 standard deviations below to 2 standard deviations above, so that would be all of this. And if I were to add up all of these percentages, 4.4, 9.2, 15.0, 19.1, 19.1, 15.0, 9.2, and 4.4, that's giving me 95.4. 95.4 of the distribution is within 2 standard deviations of the mean. So in my SAT example, that means that 95.4% of the people who took it got between a 300 and a 700. A 300 and a 700. Okay, let's do one more standard deviation. So let's do that in orange. Okay, so from -3 to 3, that would be 3 standard deviations below to 3 standard deviations above. So I'm going to add up all of these percentages from 0.5 all the way up to this 0.5 up here. From -3 to 3, within 3 standard deviations of the mean. I add all those up and I get 99.8. Practically everybody, 99.8% of the people that took that SAT got between a 200 and an 800 on the SAT. 99.8% of the distribution lies within 3 standard deviations of the mean. If you notice, there is a little bit, a 0.1% above and a 0.1% below, but 99.8 lie within 3 standard deviations of the mean. So these percentages are good to keep in mind or good to know: 68.2, 95.4, and 99.8. And I just want to talk about what a z-score is. A z-score represents the number of standard deviations a given value falls from the mean. So if we look back up at our example, you have a spot for z-scores. Right here, the z-scores. So it's the same thing as how many standard deviations above or below you are. So if you had a z-score of 1 plus 1, you were 1 standard deviation above the mean. So you got a 600 as an example. If you had a z-score of -2, then you were 2 standard deviations below the mean. So you had a score in the SAT of 300. What do you think, what was your SAT score if you had a z-score of 0? Yeah, 500. You got right exactly at the mean. So a z-score of 0 means you scored exactly what the mean score was. Okay. So percentile is something that goes hand in hand with this normal curve. It's a score that tells us what percent of the total people, whatever we're talking about, scored at or below that measure. So the mean is at the 50th percentile. So I'm just going to fill in our pretend SAT scores again, so we kind of have some context to talk about. Okay. So let's just say, before we do the one that's highlighted, let's just say that you got exactly a 500 on that SAT that I'm talking about. Well, if we want to figure out your percentile, how that works is you add up every single percent from the left all the way up to where your 500 is, or wherever your score is. So in this case, the 500. So if I add up 0.1, 0.5, 1.7, 4.4, 9.2, 15.0, and 19.1, that gives me the 50th percentile. When you get right in the middle, right at the mean, you are in the 50th percentile. That means you did better than 50% of the people that took the test. It also means 50% of the people that took the test did better than you. So let's use the example that I have highlighted for you here. Let's say you scored 1 standard deviation above the mean. So in my example with the SATs, you got a 600. So if you want to figure out your percentile, and you got a 600 on the math section of your SATs, add up all of the percentages all the way from the left, starting at 0.1, all the way up to this last one. So when you add all those up, you get 84.1. You did better than 84.1% of all the people that took that math SAT. Makes sense, you did better than the average, so you did better than 84.1% of people. So you are in the 84th percentile. Okay. And just for some context, if you take 100 minus 84, because there's 100% of people that took it, only 16% did better than you. And the people that did better than you are the ones still in the white. These people that I'm going to circle. These percentages are the ones that did better than you, but you did better than the one in the yellow for someone who got a 600. Okay. So again, percentile, you add up from the left all the way until you get to your score, whatever score you're talking about. Okay. All right, let's take a look at some examples. So example number 1 says, in a certain high school, a survey revealed the mean amount of bottled water consumed by students each day was 153 bottles with a standard deviation of 22 bottles. Okay, so what I like to do is I like to take the information that they give me and I like to put it into my normal curve. So 153 bottles is the mean amount. So the 153 needs to go right at the 0 because that's the mean amount of water, bottles of water that's drink. So the standard deviation is 22 bottles. So if I want to go up 1 standard deviation, I need to do 153 plus 22, and that's 175. So 1 standard deviation above is 175. If I want to go 1 below, I need to take 153 minus 22. 131. Okay. Let's just fill in the chart for some practice. So let's fill in at the standard deviation of 2. So 175 is 1 standard deviation above. We know that the standard deviation is 22, so I'm going to take 175 and add 22, and that's 197. And I can add 22 more to that and get 219. That would be the amount of bottles of water 3 standard deviations above. And then let's go back the other way. So 1 standard deviation below is 131, so let's minus 22, and that's 109. And then let's minus 22 again, and that's 87. Okay. Now let's see what the question's actually asking. We don't always have to fill all of this in. It was just, I thought it would be helpful since this is our first real problem. Assuming the survey represents a normal distribution, they should really tell you that. What is the range of the number of bottled waters that approximately 68.2% of the students drink? 68.2%. That's an important number. If you remember when we were talking about the percentages, we said that 68.2% lies within 1 standard deviation of the mean. So that's 1 standard deviation of the mean. That's from the -1 to the +1. These percentages in here is 68.2%. So that would be 131 bottles to 175 bottles. Choice 2. Okay. Number 2. If the amount of time students work in any given week is normally distributed with a mean of 10 hours per week and a standard deviation of 2 hours, what is the probability a student works between 8 and 11 hours per week? Okay, so we're talking about like a job that a student has. So they work, the mean that students work is 10 hours. So let's put that in. And the standard deviation is 2. So I would add 2 to get to the 1. I would add 2 more to get to the 2, and I would add 2 more to get to the 3. And then let's go backwards. From 10, I'm going to minus 2. I'm going to minus 2. I'm going to minus 2. Okay. What is the probability that a student works between 8 and 11 hours per week? Okay, so we have to put 11 in. 11 is going to go right between the 10 and the 2. So that's going to go right at the 0.5. So there's the 11. Let's highlight what we're talking about. We're talking about from 8 to 11. So we're talking about these percentages. They want probability. Probability can be given as a percent. So let's add up 15 plus 19.1 plus 19.1. And that is 53.2%. When I add all those up, 53.2%. So the 53.2% of the students that work between 8 and 11 hours a week. Number 3, we're talking about pipes and pipes that come off an assembly line. So things that come off an assembly line are often normally distributed as well. So lengths of pipes, weights of, let's say, cereal boxes. You would think that they're all exactly the same, and they're not. They're all really close to each other, which means their standard deviations will be littler, smaller, but they're not all exactly the same. So we have these pipes that came off, and the mean length of the pipe is 102.4, but they're not all exactly 102.4. The standard deviation is 0.2 inch. So some are longer than 102.4 and some are shorter than 102.4. So let's fill in what we got here. 102.4 is the mean, and the standard deviation is 0.2 inch. So let's fill in a few here. So if I go to the 1, it's going to be 102.6. If I go to the 2, it's going to be 102.8. And then if I go to the 3, it's going to be 103.0. And then let's go the other way. So 1 below is 102.2. 2 below is 102.0. And 3 below is 101.8. Okay, each one of them are 0.2 apart. All right, we want to know exactly 102.1. Okay, so it's not on our on the numbers that we wrote down, but we could see where it would fit. It would fit right here, right between the 102.2 and the 102.0. So 102.1. Okay. And then they're asking us for the percentile. So again, to find percentile, we draw a line exactly where our score is, or our length of our pipe in this case, and we're going to add up all the percentages from the left all the way up until that line. So 0.1, 0.5, 1.7, and 4.4. So that's 6.7. So this pipe is in the 6.7th percentile, meaning it is only longer than 6.7% of all the pipes that were made. So just as a frame of reference, if I did 100 minus 6.7, I get 93.3. 93.3% of the pipes are longer than this. And that's not what the question's asking, but just a little extra information. So percentile, 6.7th percentile. Choices are weird, but the choice that's going to work best is number 1, below the 16th percentile. So again, that just means that that pipe is pretty short that came off the assembly line. It's only longer than 6.7% of all the pipes that were made. All right, Liz applied to college that requires students to score in the top 6.7% on the mathematics portion. Okay, top 6.7%. Liz needs to score in the top 6.7%. So we're talking about this section because Liz needs to be in the top. So if I want the top 6.7%, I'm going to start looking from the right to find what score she needs. The scores in the test are normally distributed with a mean score of 576 and a standard deviation of 104. What is the minimum score Liz must earn to meet this requirement? Well, let's figure out where she needs to fall. She needs to be in the top 6.7%. So what I'm going to do is I'm going to start at the right, and I'm going to add these percentages. So I'm going to add 0.1 and 0.5, and that's 0.6. I need to add more. So let's add the next little section, 1.7. Well, when I add 1.7, that's 2.3%. If I add 4.4 to that, that is exactly 6.7. Works out very nicely. So Liz has to score here. So again, if I were to take these percentages, 4.4, 1.7, 0.5, and 0.1, those are the top 6.7%. Okay. So just as, I guess as to kind of help explain this, if you were to add up all the numbers to the left of that, you would get 93.3. So Liz's score would be in the 93.3rd percentile. That makes sense. Liz needs to do better than 93.3%. So I'm just gonna, this is more than you need for this problem, but this is 93.3% and this is 6.7%. So we could say, they could have said it in two different ways. They could have said Liz needs to be in the top 6.7%, or they could have said Liz needs to be in the 93.3rd percentile. It's the exact same question, just worded differently. Top 6.7% of people who take it, or in the 93.3rd percentile. Same thing. Either way, we need to figure out what score goes at this 1.5, at 1.5 standard deviations above. So let's fill in what we've got. So the mean score is 576. That's going to go right at the 0. And then let's add 104 to that, because that's the standard standard deviation. So that's a 680. Okay, so that brings us to the 1. I need to go, I know, to the 1.5. So if one standard deviation is 104, then what would be half a standard deviation? 52, right? Half of 104 is 52. So I'm at 680. Let's do 680 plus 52. And that's 732. That goes right at the 1.5. 732 is the score she needs to be in the top 6.7%. Okay. That would be her minimum score. She could score higher than 732 and still get into this college, but the minimum amount she would need to get into this college would be 732. Okay. An amateur bowler calculated his bowling average for the season. If the data are normally distributed, how many of his 50 games were within one standard deviation of the mean? Within one standard deviation of the mean is -1 to 1. Okay, so we can know what these percentages are in one of two ways. We can add up 15 plus 19.1 plus 19.1 plus 15, and we get 68.2%. Or if you remember when we first went over these, we talked about the percentages for one standard deviation within the mean, 2, and 3. So one standard deviation within the mean is 68.2%. So if you remembered that from earlier, you could have just used the 68.2%. If not, totally fine. You can look at the curve and add up those four. So we don't really know what his scores are. We're not going to put anything on here. We just know that he has 50 games, and we want to know how many of them were within one standard deviation of the mean. So we need to figure out 68.2% of his 50 games. So we're going to multiply 50 by 0.682. And we get 34.1. Well, we can't have 0.1 of a game, so 34 games were within one standard deviation of the mean. 34 of his 50 games. Okay, what I'd like you to do is we're going to do the practice that you have on your assignment 1 and 2. Okay, that's all there is. You're going to do practice 1 and 2 and hand it all in. Okay, bye everybody. Hope everybody's doing great. Bye.